The idea of a four-dimensional spacetime that Einstein used in special relativity was developed by his former professor, Hermann Minkowski, in 1908, a few years after Einstein's publication. His interpretation provided a critical precursor to the later need of tensor calculus in general relativity. In fact, if it wasn't for the help of his dear friend Marcel Grossmann, Albert Einstein would never have landed a job at the Swiss Patent Office. It was there that Einstein had a boss who encouraged him to question everything. This led to Einstein to develop his famous thought experiments, which ultimately led him to his famous theories of special and general relativity. It would also be Grossmann that would introduce the concept of a tensor to Einstein through the works of Riemann, Christoffel, Ricci, and Levi-Civita, with whom Einstein would later develop a professional correspondence with. It was through no small amount of effort and difficult mathematics that Einstein would struggle through and ultimately arrive at his rigorous treatment of his theories of special and general relativity. This series is the evolution of those ideas through the lens of tensors. Enjoy! For the spacetime of physics, we need four coordinates, the time t, and three spatial coordinates x, y, and z. We put time as t upper 0, and x, y, and z as x upper 1, 2, and 3, so that the four coordinates may be written as x upper mu, where the suffix mu takes on the four values 0, 1, 2, and 3. The suffix is written in the upper position in order that we maintain a balancing of suffixes in all the general equations of the theory. The precise meaning of balancing will become later clear. So let us take a point close to the point we originally considered and let its coordinates be given by x mu plus dx mu, where dx mu is the displacement vector. And if we choose the units of distance and time so that the speed of light is unity, then our space-time length or interval given here is an invariant. Now what this does is it allows us to make linear non-homogeneous transformations of the coordinates result in linear homogeneous transformations of the dxu coordinates. Now for any set of four quantities a sub mu being a contravariant vector, then its squared length can be written in this way, and this is also an invariant. So the concept of invariance is very important in tensors, and this again represents the squared length of the vector A. In a similar fashion, we can define the dot or inner product of two vectors A and B in this way. And this is also an invariant. So the dot or scalar product of two vectors is invariant. Now, a convenient way to work with invariance is in the act of raising and lowering indices. A covariant vector, co below, with the mu being written downstairs, can be thought of as the components of a vector here, where the spatial coordinates are negative. Then this representation of the inner product holds true. And therefore, covariant vectors can be thought of as the components of a vector. Roman indices often indicate the indices 1, 2, and 3, where Greek indices include 0. Now, if we construct the outer product, creating a tensor of rank 2, or a mixed tensor, then we can create a scalar by setting the indices upstairs and downstairs equal to each other. Indices should never appear more than once in a term. Oblique coordinates. Oblique axes. Oblique axes are ones that are not at right angles to each other. So what does special relativity look like in a set of oblique rectilinear axes? Again, oblique means that they do not form right angles. They are not orthogonal. And rectilinear refers to the fact that the axes are straight lines. So each displacement vector, dx, becomes a linear function of the old dx in the oblique axes. And this calculates the squared length, where the metric g mu nu depends on the oblique axes chosen. The metric tensor being a symmetric tensor, we can interchange mu and nu. General contravariant vector has four components, a mu nu, which transform just like the dx mu under any transformation of the oblique axes. Thus, the inner product can be defined, or the squared length of the vector can be defined here using the metric. And given a second contravariant vector, another such vector can be constructed, a mu plus lambda b mu, which may be formed for any given lambda. And so its squared length should also be invariant. If we expand this vector's squared length, we get the following result. And so since this too must be invariant for any lambda, we can make the conclusion that the coefficients of lambda and lambda squared are also invariants. So, with the interchangeability of mu and nu, we may write this expression as 2g mu nu a mu v mu nu. Now we have this quantity is also an invariant, thus we may write out this expression is an invariant. So as we can see, the idea or concept of invariance is very central to working with tensors. And if we let g represent the determinant of our metric, g is not allowed to be equal to 0, otherwise our axes would not provide independent directions. And in orthogonal coordinates, one has the following metric, so the determinant would wind up being -1. Therefore, with a set of oblique axes, g must also be negative. Now, why is this? Well, oblique axes are obtained from orthogonal ones in a continuous process, which results in g varying continuously. And therefore, g cannot pass through 0, thus g remains negative. And we have the following transformation rules to raise and lower indices here for a given covariant or contravariant vector. The inverse metric is the cofactor of the original metric, and so that indices don't appear more than once, we can expand this out and get a general idea of a transformation rule for the metric. So this mixed tensor here provides a way of a substitution method of one index row for another mu. This becomes a very useful tool in working with tensors. So now we've established a few rules here that will be useful when working with space-time coordinates. Curvilinear coordinates. What happens when our axes are not straight lines? Curvilinear coordinates, where the axes are curves rather than straight lines, will change the idea for our metric here. So consider our quantity, some quantity q. Its partial derivative with respect to a coordinate x mu is the ordinary partial derivative. We'll use a comma notation to represent this. Now if we pass this quantity from a point x to a point x plus dx, we get the variation delta q as the partial derivative times delta x mu. But here the metric are no longer constants, again because our axes are no longer straight lines. So they form field quantities from point to point. They vary from point to point. So then we ask naturally, what happens when we change coordinate systems to, say, a barred coordinate system, a new coordinate system? Then the differential transforms in the following way, using our new comma notation and noticing the barred system is being represented only on the indices here. Thus, by definition, this mixed tensor may be represented in the following way. Using our new notation. And if we apply this to an arbitrary vector, a mu, we can rewrite it in this way, showing that it certainly is a good index replacement rule. And so with our transformation rules written here, since the inner product is always invariant, we may rewrite it in the following way, and thus a transformation rule is established here. And for some mixed tensor, we remind ourselves how to transform from one coordinate system to another in our new notation here. One keeps track of the barred and unbarred indices appropriately. And so given this transformation rule, we have the metric in our new coordinate system, the fundamental metric, or the first fundamental form. Now, if we take a scalar field quantity and let it be viewed as a function of our coordinates x or our barred coordinate x, then we may write the following transformation rule for our scalar quantity. And we see that the derivative of a scalar field actually produces a covariant vector field, a covariant tensor. And this is the motivation behind the name covariant derivative. More on that later. An essential theorem for tensors is the quotient theorem. It's a test for tensor character. And suppose we have a tensor here such that this product gives us another tensor. Well, we're testing P to see if it is a tensor. So we're using an arbitrary tensor A, and the product we're saying is a tensor, so we must see that the tensor P transforms under the proper transformation rules for tensors. And so following through the calculation here, we see in fact that it does transform properly under the rules of transformation for tensors. The quotient theorem is a powerful one to test for tensor character. Next, we discuss curved spaces. The invariant distance ds between 2 points x and x plus dx is ds squared equals the metric times dx mu dx nu. And ds is real for what we call time-like intervals and imaginary for what we call space-like intervals. Time-like intervals, the velocities multiply to a positive, where space-like, the velocities multiply to a negative. So here, although the g, mu, nu, the metric are not constant, the curvilinear coordinates where g is given as functions of these coordinates, that network of curvilinear coordinates will fix our metric functions, and therefore it'll determine not only the coordinate system, but fixing the metric, it also determines the curvature of the space. We now must discuss something called parallel displacement. So suppose we have a vector a mu at point P, and if the space is curved, like standing on top of a hill, we cannot give it meaning or give any meaning to a parallel vector located at some other point Q. These vectors would definitely not be pointing in the same direction. However, if we take a point P prime, which is really close to P, with an uncertainty to second order, that meaning that the distance from P to P prime would count in first order, we can define the concept of a parallel vector, a linear approximation for a small displacement. So, we can give meaning to the idea of a vector a mu being parallel to itself after being transported from P to P prime. Then, if one conceptualizes taking a step-by-step motivation through a path, we can construct a path continuously using tangent vectors continuously parallel displaced along the curve. But note, there's no absolute meaning of a parallel vector at the point Q. So if we parallel transport a vector, say, around a closed loop, we will end up with a vector back at point P, which usually points in a different direction. The amount of twisting that the vector experiences is called the holonomy. For a flat surface, the holonomy would be 0. So how do we obtain equations for parallel transport in a curved space? For this, we will take an extrinsic point of view, that is, looking from the outside in. So let's imagine that our four-dimensional physical space sits or is immersed in a higher n-dimensional space. Capital N is the dimension of that space. It's an ambient space. And in n space, we introduce rectilinear coordinates, that is, straight line coordinates, Zn, where n ranges from 1 to capital N, but not necessarily orthogonal, just rectilinear. Between two neighboring points, then, there exists an invariant distance, ds squared, equal to this value where h and m are constants or scale factors given in our coordinate system for nm ranging from 1 to capital N. And because these are constants, they allow us to raise and lower indices in the following way. Therefore, the squared distance may be written as follows, and physical space can be thought of as forming a four-dimensional surface in our flat n space. So now we have constructed the idea that a surface, a four-dimensional surface, can be constructed in this higher dimensional n space. And if we imagine each point, x, in the surface, it determines a definite point y in n space, call it yn, which is a function of x's. And the equation for the surface would then be obtained by eliminating the four x's from the n equations of the form yn. Therefore, there will be n minus 4 such equations. If we differentiate the y's with respect to the coordinate x mu, we have this partial derivative formula. And if we transport from a point x to x delta x, we have the following change in coordinates for y, and thus the squared distance may be written in terms of the y's, or transformed back in terms of the x's. Lowering the index here allows us to rewrite the expression in terms of the x's here, and because we know that the squared distance is the metric times our differentials, we can equate that our metric here is given by this formula in terms of our y's in n space. So now let's consider a vector, a mu. The components of this vector transform like the delta y's in n space. Therefore, we may write this transformation law. This vector lies in the surface using parallel displacement to a neighboring point. What's going to happen? Well, if we shift this by keeping it parallel to itself in a curved surface, again, we understand that that vector would not be parallel to itself anymore. That's due to the curvature of the space. So, what do we do about this? We can project this vector onto the surface to get a definite vector actually lying in the surface. So this projection process is as follows. You take the vector and you split it into two parts, its tangential part and its normal part. And then we discard the normal part. So here, splitting the vector into two parts, a tangential and a normal part, let the vector k mu denote the components of the tangential component part of this vector. Therefore, it transforms as follows. And since all the tangential components are orthogonal to the normal ones, this equation holds, so we can use it to multiply the vector an, and we get the following result where the normal part drops out. Thus, for the vector k, transforming in linear approximation here, our projection process produces the following result. So we have a parallel transported result of a nu. If we now take the difference between k nu and a nu, we get the differential dA nu, written in terms of the x coordinates. Well, that's it for this part of the video. Please stay tuned for chapter 2, and I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.